Hello everyone, welcome back. So now in this video, we'll be talking about AI short notes. So let's get started without any delay. So this is going to be a very important session for like the GADA exam, and we have covered most of the things which are going to be very important. Plus some extra things are being also included so that you do not create some silly mistakes or misconception, which can help you actually avoid any silly mistake in your main exam. Okay, so let's get into straight into the thing. Cool. This session is going to be smaller than the earlier subjects, other subjects short notes, because it's already very too small of a syllabus. So yeah, so I'll will straight get into the uninformed blind search, or basically uninformed search. Why blind? Because we do not really have any idea about or any extra information about the search space. Okay, uh, any extra information about the domain we are solving. So that's why it's called the uninformed or blind search. Now we have most prominently four important algorithms, name being breadth first search, depth first search, and uniform first search. Lastly, iterative deepening first search. How does breadth first search works? Uh, at each of the other level, you first look at each of the neighbors. That means for each of the parent node, you'll be looking at each of the child node a parent node is having, and then you get to the child of the other level. That means for the first level, what are the second level nodes? You'll just explore after exploring all the nodes within the first level. So each of the child would be explored sequentially like that. Okay, so it expands shallowest node first. Time space, that is all already existing in the next slide, so would like to avoid it right now. Depth first search would not care about what exactly is the neighbor. If I have a child, let me go to the child. If there again exists a child for a node, let me go to the child. This way it keeps on going and going and further expands the deepest node first. Okay, uh, so breadth first search is using the queue to help us track of what are the nodes in which order we should be, exploring. In DFS, we actually do not use, but by default, the recursion takes place. And if you want to use it's going to be a stack which is being used as a data structure to handle all that. The third is the uniform cost search, in which what happens is we actually go by the idea that what exactly is the cost until now, when while exploring. For an example, if I have come until fifth node, what is the overall cost I have covered until now for reaching this fifth node, and what are the again minimum set of like low cost path I'm having. Whichever is lower, I would like to explore that path, not knowing about what lies further in the future. So we actually try to decrease the overall path cost until this point where we actually stand, and that's how we actually keep on expanding the nodes further. Okay, and what exactly is iterative deepening first? Iterative deepening, DFS. It's DFS, but we wanted to take some motivation from BFS as well. So what we do is we do DFS iteratively at each depth. So at D is equal to 1, depth first search is run. At D is equal to 2, depth first search is run. At D is equal to 3, depth first search is run. And that's how we keep on going further and further. Now, how does it really help? So in DFS, we actually go to the deepest node first, not knowing about the neighbors where I could have an optimal solution lying in the earlier side of towards the root node itself. So we avoid that. So we wanted DFS to actually travel all that first, then go to the next level, then try all. So that's how the advantage of DFS plus BFS is being merged to give rise to iterative deepening first search. Now, with respect to the time, space, optimality, and complete, first of all, let me just talk about the optimality and complete idea. So, optimality is much more about would the solution returned by the algorithm be optimal or not. Complete actually tells me, will I be getting a solution or not, is the question over here. Okay, so I hope you understand that the completeness is in doubt for just DFS. The reason being the overall state space I'll be having. because DFS explores the overall state space. If I'm having lesser space with me, in that case, DFS will not be able to find out the solution. Okay. With respect to the optimality of the algorithms, what actually comes up handy over here is that what exactly were the cost which were being used over here. So if the cost is what should I say, uniform cost, or it's the same cost we are having, in that case we will be able to find out faster. Otherwise it actually suffers. We might get suboptimal solution, we might reach suboptimal solution in that case. Okay. Now with respect to the time and space complexity, you can see over here, it's pretty much straightforward over here. M is the maximum depth, and D is the depth until which we are going. B is the branching factor. Now just one critical thing over here with respect to the UCS, why we are getting this 1 plus CYE. So C is telling me overall cost to reach my optimal solution, where E is the minimum cost minimum path cost I had throughout. So it is actually telling me, say, like, what do we keep in the power of B? We generally keep how many nodes are getting explored. Okay. So what exactly, or basically how many levels are getting explored. So the idea is whatever is the overall cost to reach my final, what should I say, solution state, divided by total cost divided by the minimum cost. If I do that, I might get my overall number of levels I traveled. So that's how it gives me that overall. And it's like right now written C by E, but it has to be floor of C by E plus E1, which would be returning me overall time and space complexity for this. So that's our uniform cost search. Moving ahead, so everything is being already considered over here. You can just read through this. Now we get to the idea of informed search, which is the heuristic search. It uses the idea of that, okay, what is going to be my overall idea for can I do better? Do I have some extra information? Now within that, yes, we do have indeed some information in form of heuristic function. Now what is a heuristic function? Heuristic function try to estimate what is going to be my overall cost from this particular node where I'm standing until my last goal node or state, if I'm talking about. So there was this GN which was already existing in uninformed search, which used to tell accurately, because we actually traveled that path. What is the path? What is the total cost until this node from the starting node? What is the total cost? Heuristic tells me what is the estimated cost starting this node until the goal. So overall, GN plus HN can give me the overall idea of what would be my overall estimated cost of reaching the goal state from my start state. Okay, that's how we actually bring in the concept of heuristic function. So best first search expands the nodes based on the evaluation function. So whatever Fn is going to tell, best first search uses that thing. Okay. So over here, if I just talk about it, does not if I just so Fn, so best first search is an overall idea. It's a higher category. Now within that we have some variants which we need to talk about. So wherever Fn value is lesser, we just go by that particular node to be explored. Okay. Now greedy best first searches in which Fn is just equal to Hn, your heuristic function, no use of GN. So that means you actually go by whatever is the estimated cost. Wherever this is minimum, you would like to just expand that particular node. Okay. So it's not optimal, susceptible to loops, because you are not really considering what exactly is the cost until now. So you might just keep on looping around. uh, Not a good strategy. A star search, the best algorithm on which we actually get to see most number of questions as well, around its definition as well, uses Fn is equal to Gn plus Hn. It is also best first search, which actually uses minimum Fn to evaluate which nodes to be used. Okay. So it combines the path cost until now and the heuristic cost, which is estimated cost. Now there comes up two important terminologies, which is admissibility and consistency. What is admissibility? So we are using a heuristic function. Now the estimated value of the cost to reach goal state from any particular state should be, or from a node should be, lesser than or less than equal to the actual cost which we are not aware of. Because if we know, in that case we could have used directly that thing, but we don't know. So what we are saying is, what should have been or what would have been the true cost, it should be, the estimated cost should always be less than or equal to that means we always are optimistic that it shouldn't be worse than this, something like this. So we want to be optimistic always. So a star search, sorry, so the heuristic function never overestimates, it is always optimistic, and it ensures optimality for the tree search. Okay, within tree search, admissibility condition is just sufficient to check for while solving the problem. Okay, while checking that whether a star search would be able to give me optimal solution or not. If the hn is admissible, in that case it's fine. Okay, so point to be noted, admissibility is telling me about overall cost from any node to the goal node. Okay, what should be, it should be lesser than the actual cost. Now there exists the other one, consistency, another property, which is the same as admissibility for tree search, but for graph search it is not. There we have an added complexity, but it is a kind of a, what should I say, a kind of a strict form of admissibility, like in layman language, if I want to say. So consistency property tells me, or it talks about the estimated cost of a path rather than the overall estimated cost of the overall, what should I say, from this node to the goal node. But this one actually talks about an edge, sorry, estimated cost for an edge, what should it be? So if you want to find out whatever, so let's suppose a and b are connected, so let me just write it over here. So if a and b are connected over here, okay, I know it has some ha, it has some hb, and there is some true edge cost which exists. Okay, so what we want is that the hn, that means the cost from this, should be less than equal to this cost plus whatever is the estimated cost from this to reach the goal state. So yeah, this makes sense. It's nothing but it's telling me that what is the overall cost from this to my goal state, and this is telling me what is the overall cost from reaching to this. So what we are saying is, this should be less than this plus this, a kind of triangle inequality. This must follow, and this is a string, like a very important condition to be checked for graph search wherever we are using a star search. Okay, so it's, as I mentioned, it is nothing but a kind of triangle inequality and a form of strong admissibility for the graph search. So it should also hold true. And we had a question in previous year also where a question was asked on this. So you should definitely revise that if you are not aware of. So these are the two conditions, and then it's very simple. We use as priority queue to maintain what are the like open state, closed state, and in order to maintain the min fn cost node always in the front. So that's the idea around the A star search or the overall informed heuristic search. Next, what do we get as adversarial search? So in adversarial search, we are having two agents playing against each other, kind of a thing. So it's like you are having tic-tac-toe game. So you are competing against someone else. So the idea is always to maximize gain for yourself and to expect minimum gain for the opponent. So that is the idea. So the most prominent algorithm being used is min max and the alpha beta pruning over here, alpha beta min max algorithm. So min max is very simple. So like, like what exactly is going to be the overall cost. So with respect to that, like, because what exactly is the potential cost of each step you take or your opponent might take, then you keep ahead, like keep going further trying, and then you estimate whether you lose or gain. Depending upon that, you try to evaluate each of the node, and then you actually play the best possible, what should I say, a step for you, best possible turn for yourself. That's how you play that according to yourself. Okay, what is the time complexity? So b is the branching factor, m is the maximum depth, b to the power m space b into m. Makes sense, similar to the initial search algorithms which we talked about. Now, why alpha beta pruning comes into the picture is a very important thing to actually learn by itself. So, alpha beta pruning is there for to avoid some of the branches which are simply, what should I say, which shouldn't really be tried, which can be simply avoided. So we should be eliminating those branches which cannot influence our decision. Okay, now over here we use two important parameters, alpha and beta, which are being learned step by step while going from like the leaf to while going up. These are being learned, and some of the branch it helps in actually simply removing those. So alpha beta is a range in which we actually want our value state to vary. If alpha beta range actually the condition for them, if it breaks, in that case we simply come out of or basically we leave the branch. So the idea is alpha should be less than beta, most like that's what we actually want. And if in any case we get alpha being greater than equal to beta, that's where we prune the branch. And similarly for the state value as well, if we find out that okay, we are not getting a value, what should I say, we are not getting, sorry, we are getting the value within the branch, sorry, within the interval, in that case we might be fine. But if it is outside, in that case we have to actually prune it up. Okay, now there is a complete what should I say, complete algorithm which we have solved and discussed within our IC lectures as well, which you can just try. Okay, so it produces the same result as minimax, but it is just more efficient. And the performance actually depends upon the ordering of the node. Okay, now when I say the ordering of the node, what actually changes in that case is the overall time complexity changes to b of m by 2. Why b of m by 2? Because we tend to know that in the best possible case will be removing a number of branches. Now like there is a proper what should I say, heavy lifting for derivation thing, like not required right now, but because we are avoiding a number of branches, we tend to say the overall effect of pruning the branches reduces to m by 2 of the depth. So that means the overall running time complexity would become b of m by 2, b to the power m by 2. So that was all about our alpha beta pruning as well. Okay, now we get into the logic, and that too propositional logic. So we'll talk about what exactly is being like what's important. So connectives in summary. So there, so in general we have conjunction, disjunction, not, and then we have implication and by implication. Okay. So what are the symbols? You can see all those as well, and the translation hints, because the English translation is also used. So P is a logical variable we will be having, which will be determining a statement. And if negation of that we are saying, that we say that that does not hold true. It is not the case that this is true. Okay, P and Q would require both the statement to be true in order to conjunction to be true. P or Q would like to see both as not true to say the disjunction is not true. Okay, implication. So I have already discussed this in detail as well while solving the problems. So it goes by this idea. So P implies Q. The only case where P implies Q becomes false is when this is true and this is false. This is the only case when P implies Q becomes false. Okay, and there is a strong reason behind that. Like I guess we have discussed it. So we can say, like for an example, if you work hard, you'll succeed. Somebody would be able to claim that I am false or my statement is false if they complete the requirement but not able to get the result what I said. So they did hard work but did not succeed. Then only they'll be able to say that this is false, what you're saying. Okay. But if they're not just studying, then even if they fail or succeed, that would not be really like lying in my zone. My statement would still be always true in that case. Okay. So always remember, P implies Q would always be false only for the case when P is true, Q is false. Okay. So there are some statements, and we have some translation idea as well, which we'll talk about. Biconditional. Biconditional is actually both ways. You can write this way and this as well. Sorry, let me write Q implies P. So this would be true when this as well as this true. So that means what I'm saying is this is actually true when both are true or both are false. If true false or false true case exists, in that case it becomes false. So only it's like what should I say? Uh, uh, so it's like a similarity check whether P and Q are same or not. So when they are same, then only P by conditional Q would be true if they are exactly same. Okay, and then some of the English translation hint, and we will see those further as well. So let's move on to the next one. So some logical equivalences. Point to be noted, very important. So P implies Q has a proper formula which you shall use while deriving a number of expression, while saying whether a particular statement is valid or not with the reasoning. So in that case, you must use this kind of thing. And as I mentioned in the RIC batch as well, that P implies Q is exactly same as its contrapositive, which is negation of Q implies negation of P. Okay, so we would be requiring this a lot many times. Okay, then there is something known as converse, which is nothing but so see, there are three things. Let me just bring it up. So if implication was P implies Q, then we talk with respect to this only. So what is the converse, what is the inverse, and what is the contrapositive? So the converse of P implies Q is Q implies P. The inverse of P implies Q is negation of P implies negation of Q. And contrapositive is actually combination of converse and inverse. So negation of Q implies negation of P. And we know these two are always same. Okay. Then we have De Morgan's law, which actually changes the conjunction to disjunction, disjunction to conjunction when applied on the overall expression. The negation is applied. Okay. Distributive law distributes the conjunction and disjunction accordingly, as you can see within this example over here. Some important rules. This is very important. So what do we mean by this rules of inference? So I have just specifically picked up these. This is telling like this. So if I assume P implies Q to be true, P to be true, what we conclude is Q is also true. So you know this. If I'm saying this is true and P is true, if this is true and this overall is true, Q has to be true to say this was true. So I hope you get this. So these are nothing but some rules of inference or inference rules. Similarly, if I'm saying P implies Q and negation of Q, this is not true and this was overall true. If this is not true, if this is false, I cannot make this as true, because true implies false would be false and this will become false. So in that case, if this is not true, this also has to be not true. We know that. Okay, some inference rules. And similarly, we talk about P or Q, negation of P or R, we say Q or R. So over here we are saying this is true, over here we are saying this is true. So like I hope you know how to go about this. So you can just write something like this. Let me just use that idea only. So this you can write as P implies R. This you can write as a negation of Q implies R. This you can write as negation of Q implies P. I hope you can see the difference. Like, I'm just using that idea that P implies Q can be written as negation of P or Q. So this one, I have written Q first and then P later, and then double negation of Q. One negation I'll keep for this, and one negation for converting this to implication. So I wrote this. This was direct, and same as this Q or R, double negation, one negation to this one, and one negation to keep for a negation of Q or R, which will be Q implies R, something like this. So you can see negation of Q implies P, P implies R, both are true. Then in that case, negation of Q will implies R. So yeah, we know that. So simple inference rules over here. Let's move on to the next one. So simple translation rules with respect to the propositional logic. Very specifically, I would like to focus on this one. This is very important. There had been a question, and though it was for GATE computer science, but it's really important. Okay. Yeah. And yeah, over here it's not written for this one. For this one, we have if and only if written as this, or necessary and sufficient and sufficient. Okay. P is necessary and sufficient for Q. Q is necessary and sufficient for P. Both are one and the same thing. Okay. Now, if we have just one, that means Q is necessary for P. In that case, it means we have to write P implies Q. If we say Q is sufficient for P, in that case, we have to write Q implies P. Why is it say? When I'm saying Q is necessary for P, I know that Q would be required always for P. That means if P has occurred, that means Q was definitely there. Okay, so that means P implies Q. Now, when I say Q is sufficient for P, what I'm saying is Q alone can handle P. That means if Q done, then P would be also be done. So I hope with respect to this, it's clear. Either P or Q. So there generally comes up two kind of variation. One is inclusive OR. That means when both are same. Okay. So like both are true. So that is P or Q. But sometimes we want exclusive OR. That means we do not want them to be same. So in that case, one of them only has to be true. So for that, we have this expression. Rest, P unless Q. This also we have solved already in our RIC also. P unless Q means negation of Q implies P or Q. Okay. Yeah, we had something over here. P is necessary and sufficient for Q. P if and only if Q, or Q if and only if P for biconditional. Okay. Now we get into the first order predicate logic. Now, what do I mean by predicate logic or first order logic is now we will be having kind of a function which takes some variables and then determine whether it is true or false. Earlier, we had the variable which had the value of true or false. But now we will not be having a variable. We will be having a function kind of a thing which will take some variables which will determine whether this value is true or false. Okay, now we have to use quantifier because now we will be quantifying the number of objects or subjects which we'll be dealing with. For that, we have universal quantifier and existential quantifier. Universal tells about all the existing ones, that means for all x, for every x. Existential, we always talk about some bunch or at least one. So let me just write, it also means at least 1x. Okay, there exists an x, for some x at least 1x. Okay, now there are some translation rules. So by default, always remember whenever you are using universal, always for all would come up, and there would be always there will be this implication would be coming up. Okay, because whenever you talk about everyone, you are giving a rule that it will always hold true. So an implication. But whenever you are talking about existential, that sometimes it happens. In that case, you are saying that there are certain things, certain situations in which this would only happen. It's not very general. So that's how you bring and over there. So for all, you bring implication. For there exist, you bring and. Now there is the negation of these two as well, which if you use the quantifier changes, and then for the sign how does it change. So if that is the case, P implies Q is there. In that case, it can be written as negation of P or Q. And when negation goes inside, it will become negation of P, or will become and negation of Q. So Px or negation of Qx, and for all was changed to there exist. Similar to the following one. I hope it's clear. Okay. So I hope you can see this beautifully, that you can write this over here and this over here, because when we are saying negated existentially, we wanted to say no PRQ and something like this, that not there exist a case where P and Q are true, and it gets changed to for all the X. If there is P, that means there is no Q. Okay. Oh, that got copied. Okay, so quantifiers got copied. Sorry for that. Okay, so we'll focus on these two things. So you have already learned negation rules and first order logic. That how do they convert to each other? Now, I guess yeah. So we have this one only as the important part over here right now. What is the pitfall over here in predicate logic? So wrong connective being used. So using and with for all, very bad, as I suggested. Why? So we have to use implication for all, and for there exist we have to use and a very beautiful example is also shown, that all dogs are brown does not mean for all X dogs and brown exist. Okay, so it's a different thing. So both are very different. For all X which are dog which are brown, they would be like true. Okay, so not really a thing. Okay. When okay, so you can think of some case as well where this when you'll say that, oh sir, why these two are not true. So all dogs are not brown, so all dogs are brown, this is what we are saying. But if I mean that, that means I'm saying there should be no dog of other color. This is what we are saying. Okay. So definitely what I'm saying is, yeah, one more thing. If there is something which is not a dog and brown, still this statement would hold true. I hope you understand that. I'm saying all dogs are brown. That means I was talking about only dogs. But if I'm saying I there is something which is not a dog and that's brown, this still holds true, but this will become false over there, because dog X would be false. This is true, but this would overall become false. I hope you get this. So that is the problem. And similarly, you can think about this one as well. Why with there exist we will never be using implication but and only. Now order of quantifier is very much important. So for all X there exist Y loves XY means that everyone loves someone. Okay, very important. But if you change the quantifier there exists Y for all X and then write loves XY, what does it mean actually is uh, for all X. Okay, so yeah, let me just think about this is over here. So we have changed the quantifier. So first of all we'll be going by Y, that there is some who is loved by everyone. I hope you're getting. We are saying Y, that means Y is being loved, but by whom? Everyone. So over here we are saying everyone loves someone, and over here we are saying there is someone who is loved by everyone. Okay, there is specific person that everyone loves. Yeah, everyone loves. Yeah, loved by everyone. Okay. Now some translation rules before moving on to the reasoning under uncertainty over here. So all ARB, you know this. So point to be noted, do not bring this up. Okay, this is correct, this is bad. Some ARB we have to use this. No ARB. Yeah, this is very important. If somebody says no ARB, people might get confused. So you have to say negation, sorry, for all A, for all X, whenever AX is true implies negation of B, or equivalent you can say no ARB. That means there exists not a case where A and B are true. Okay, so you can write it like this as well. We have seen this for exactly one. So we have seen it in RIC as well. So you would determine that there exists an X and there for all the Y, and then you'll conclude that Y and X are nothing but same. So in that case, it's saying that there is one only, at least one X, sorry, at least one case. If I am talking about, then this alone is sufficient. There exists X PX. So that was all for the logic part. Now we'll get into the reasoning under uncertainty. Okay. So very simple. We use the Bayes theorem for this. Okay. We use the idea of conditional independence dependence. The Bayesian networks, we create some directed acyclic graph. Okay. Uh, so the nodes are being represented by the random variable, and edge represents the influence, the conditional dependency or independency. Like we need to just understand after drawing the graph, which we have already seen. But yeah, overall edge actually determines the influence X can have on Y. Okay. Now we generally try to model at last, because if we have a number of random variables, what we want to model is the joint distribution. Now while doing so, what we want is like, how do we calculate the joint distribution? One is I can simply consider them to be independent, but that's not the case. But if I know how all the conditional dependency comes into the picture, I can still model it beautifully using the Bayesian networks, which actually tells that it would be a product of p of xi, that means the current feature or the current random variable given its parent, and then so on, so on, so on, until I have a node which does not have any parent. So for that, there would be no condition. That's how we actually write the joint distribution. Okay. Now how do we evaluate? So this is something which we want to evaluate. Now how do we do it? So there are two methods: exact inference, approximate. Now exact inference means we would like to calculate the exact probability by using variable elimination. Now what do we mean by variable elimination? Is we do not want some of the variables, because it might be that we have x1 to xn variable, but I want the probability of x1 x3 only. So in that case, I do not want x2, and from x4 to xn are not required. So how do I get rid of those? Is the variable elimination method, when I want exactly the probability of x1 x3. Okay. So within that, what do we do is, the overall idea is also written: calculate the posterior. Like how do we generally write the query, write the evidence, form the factors, find out what are the factors from CPT, conditional probability tables and evidence, and sum out on the hidden variables. For an example, just giving you the brief idea, if you wanted to find out just x1 x3, what you'll do is x2 comma x4 x5 up to xn. You'll sum it up and you'll get this. So for this probability, joint probability, if you sum it up, you'll get for all the x2 values, x4 values, x5, xn. If you sum it up, you'll get a probability of x1 x3, whatever is being asked to you. Now over here, instead of this, you'll be using a kind of this expression, which will be helping you solve it a little faster, due to the a simple factored multiplication you'll be having. Okay. And then you'll normalize the result. You get the final output. Okay. So that was the idea. So normalize the final result. That means like given some condition, because we generally use whenever we are, yeah. So we had some E condition over here. So if I'm saying E equals E, so we will be dividing it by probability of E equals E. So this is the normalization part which is being referred over here. So this is exactly the variable elimination method. Now to go further, we have next approximate inference, in which we do not really we try to approximate this inference with the help of sampling. So we sample the random variables, and then with the help of that, we actually try to approximate this inference. This is being used when we have very large networks, Bayesian networks, okay, where exact inference can be too slow and be hard. Okay, so different methods are rejection sampling, likelihood weighing, and the Gibbs sampling. Okay, so these are the three methods which comes in the syllabus. Rejection samplings, that we generate samples from the prior distribution, and the samples which does not corresponds to the evidence, we reject them. Okay, the problem is it is inefficient if the evidence itself is very rare, because ultimately we need to find out something like this, and if the evidence itself is very rare, we will be very we will not be able to find out the evidence probability in that case. So that's the idea for the rejection sampling. Now, if I talk about likelihood weighing, so what exactly happened within this? So what exactly goes for the likelihood weighing is, we fix all the evidence variables. We are not going to sample them, but the variables which are non-evident, we actually sample those, and we try to calculate the weight of each of the sample by the likelihood value of the evidence given parent variable. So like, this is how we actually calculate it. And there had been a question which exists in our RIC course as well. You can just check out that. That will help you understand how do we calculate all this. So we actually calculate the weight of each of the sample depending upon how the likelihood comes up. And we call it weight, not a probability value, because for the other variables we do not really consider calculating their probabilities. We just make it one and calculate only for the evident variables which were required. Okay, and which are required in the evidence variable. For others, we just leave it as it is, and that's how we calculate the weights. And then lastly, we actually calculate based on the weight, sum of the weights divided by sum of the weights where evidence was true. We get the overall what should I say, conditional or posterior distribution value. Posterior, not distribution, posterior probability. Lastly, Gibbs sampling. And now, if I talk about this one, what do we do in that? Also, it's similar to the first, the previous one, uh, where we actually do likelihood weighing. So we fix the evidence variables. We randomly initialize the non-evidence variable. Okay, we iteratively sample each variable xi conditioned on its Markov blanket, because there is a proper Markov chain kind of a thing coming up. So that actually comes up. So we iteratively sample each variable conditioned on like the previous parents and the parents, something like this. And then we actually get these samples. Okay, now this is how basically the sampling, like we'll be calculating the sampling, and then with the help of, we'll be doing the sampling, and how that's how we actually come up with the posterior probability value. Now there are some pitfalls over here which I would like to talk about again. uh, so like likelihood weighing versus rejection. Likelihood weighing does not reject samples, it weighs them, which makes it much more efficient than rejection sampling, because in rejection sampling you simply reject if evidence was not there. Okay, in Gibbs sampling, so there is a burn-in period, very important for Gibbs sampling convergence to take place. So we get the true kind of a distribution or values only if we get the stationary distribution, but that still takes time because of this Markov blanket idea, Markov chain process. So we keep sampling until it gets converged, or basically we get to the stationary distribution, and then only we use it further. Okay, what is independence in sampling? So Gibbs sampling produces samples that are dependent on previous sample, not the independent sample. Okay, so for Gibbs sampling, it is very important that we are getting sample dependent from the previous sample, because it actually uses what is coming up like in each iteration from the previous one, because that is being used to determine the new one. Okay, so that was the overall idea with respect to the sampling and all, and that was the reasoning under uncertainty. We have solved a good number of questions again there as well. So you would be enjoying that. If you have not tried, if you have not seen that, please try them. Look at those. That was all within AI Thank you guys for watching this session. Would not take much time, giving away some time back to you so that you can revise the subjects. Thank you.